When Newton created his laws of motion, he gave us a way to describe how a particle gets from one point to another. What he didn't explain was why the particle chooses to take one path over another. Unsurprisingly, much like why I might choose watching TV over taking a run, the answer is energy. Just like you and me, particles are lazy and desire to expend as little energy as possible. The total used energy of a path is the kinetic energy it uses to climb up, minus the potential energy it gains with height. This is called the action of a path. The path with the least action is what we observe as the path the particle takes. In quantum mechanics, there's still the consideration of these different paths, but instead of the particle just taking the path of least action, quantum mechanics says the particle could very well take every possible path. But how? We can explore this with a simple question. Does light go in straight lines? We can draw an infinite amount of paths that a light ray may take to reach the detector, but let's just make a few for now. We will use an arrow to represent the probability of a ray reaching the detector. These are called amplitudes. Each amplitude has a length and direction. The length of each arrow represents the probability that a ray on that certain path will reach the detector. As you can see, all the paths eventually make it to the detector, so all the arrows must be the same length. Of course, some paths are shorter than others. That's where the direction of the amplitude comes in. Let's imagine a stopwatch. We start the watch when the ray leaves the source and stop it when it reaches the detector. Whichever direction that arm on the stopwatch is pointing is the direction of the amplitude arrow. Essentially, paths that take different amounts of time point in different directions. Now let's say we draw out the amplitude arrows for each of these paths. In order to find the overall probability of any ray reaching the detector, we must add up these tiny arrows. We do this using the tip-to-tail method, where we put the tip of one arrow to the tail of the other. You'll notice that arrows that point in different directions, like A and B and F and G, cancel out, which means that they don't really add to the length of the final arrow or to the probability of the light reaching the detector. In our situation, each crooked path has a path near it that is shorter and straighter. These differences cause stopwatches pointing in dramatically different directions. However, at a place where the paths all become mostly straight, say around path D, the time and therefore direction of the arrows are similar. That means the arrows add up rather than cancel out. That's where the light goes. So unlike in our classical example, quantum mechanics allows light and particles to travel all possible paths, but makes the path of least action the most significant. Hey!